Okay, let us continue. Today we will continue discussion of Bethe Ansatz for spin chains and maybe also for Gaden models. These are in fact main examples where algebraic Bethe Ansatz works, and so I would like to write down concrete formulas and some explicit expressions once again. First of all, I should recall the idea of what we did last time. The idea and main result, just shortly, briefly. So let us write it like. We discussed Bethe Ansatz, which was the way how to construct solution of quantum problem. And main idea was the following. We had our transfer matrix, which we denote like T, and it was ABCD. And this element B played a crucial role. We used it for construction of our solution. We defined a solution like a product of these B's from U1 to UM acting on vacuum vector. And we try to understand if we can find a solution in this way. And what was the result? So let me also recall we used two functions, G, which was h over z minus w, and the function f. These two functions were elements of R matrix, z minus w plus h over difference. So we had these two functions. We had this formula for Ansatz, and we also had functions a and d small, which were just the products of all corresponding elements. I will recall it a little later if you need. But let me recall the answer. So the answer was the following. We found the answer in the following way. That just a second. That this, first of all these UKs are called Bethe roots and should satisfy Bethe equations. And if it is true, and this is a very important formula, and M is a number of turned sides, turned spins, I'm sorry. So we have some set of spins, say n, in our spin chain, and this vacuum vector contains the product of all possible spins up, and we are looking for solution corresponding to a situation when m spins are turned. Okay, and the result can be written. Sorry?
The formula in the
This UK, UJ, and this is UJ, UK.
Two functions. One is G, one is F.
Uh,
So A represents G. So
no, this function f enters here, and are you asking about A and D? Yes, so let me write it. But I just so we had the action of this T was a transfer matrix, and each Lux matrix contained operators alpha, beta, gamma, delta, and the action of this, for example, the action of this alpha on vacuum vector was given by some function alpha without head, alpha I without head, and all of them depend on spectral parameter. So our vacuum vector by construction was eigenvector for these operators, for alpha and in fact for delta also. And it was annihilated by this
sorry, maybe I didn't express myself clear. This formula. Please look at the reflection.
Sorry?
I mean this formula, right?
Yes.
Yes. The upper, the dominant is G.
It is H divided by Z minus W.
I mean, if you look at what you are writing, it's F divided by F.
F, yes. So what is, say it again, I just don't understand the question.
The formula in this bracket, in this box,
Yes.
No, not this box, just some up. Lower.
Here.
No. I mean, this is AUK divided DUK, right?
A divided by A of UK divided by D of UK.
Yeah, this should be equal to G divided F, right? Not F divided F.
No, this is just equal to this product. This is a result of what we call Bethe equation. Maybe I don't understand your question.
This both of this place should be F, because you look at this. If the blue were, if this were -1 or what?
Are you saying that we had a difficult answer, or what?
No, I mean this should not be F. It should be G, right? G is divided.
No, this is maybe you are talking about a formula for eigenvalue, but this is a formula for Bethe equation. So we finally found that. Just a second. Just a second. eigenvalue for generating function for eigenvalue, the eigenvalue depending on t of z was given by formula. If you remember it, it was looking like it looks like a by lambda plus d by lambda tilde. Yes, you may look at your notes and maybe you will find it. But I will recall you these formulas once again when we discuss concrete example. This is what let it be just recalling. This is just some material from the previous talk, and now let us discuss some application of these results to concrete XXX spin chain. So it's a rational case, and what I mean is that we study the monodromy matrix, which was given by a product of all matrices. And it can be also, in fact, multiplied by the so-called twist matrix. I don't remember if I explained or not, but when you have RTT relations or RLL relations, then, in fact, they are, so you may look at it as a definition of quantum algebra, where for matrix elements of the Lux matrix. But sometimes some R matrices satisfy also the same relation for some constant matrices G1 and G2, for some constant matrix G, which is called the twist matrix. So we think of it as just some diagonal matrix G1 and G2, and since it satisfies the same relations, then it can be also used for constructing the monodromy matrix. This is why we can multiply our monodromy matrix by this matrix also. And we are going to include these elements into Bethe equations finally. Now we may consider the case when this L matrix is like this. I will write now eta instead of h, but it is just the same, in fact. And all this is equal to 1 plus eta like this. This was our definition of Lux matrix, which satisfies these RTT relations. But maybe it's better to write it in a different way. This R matrix can be written from another side. In unitary case, it is the same, but let us write it like this. Okay, now so we have to calculate finally eigenvalues of some Hamiltonians related to this model. Let us find these Hamiltonians, let us calculate it explicitly. This is our first problem which we are going to discuss today. This is a monodromy matrix, and we are looking for the transfer matrix, which is a trace of all these expressions. So we would like to formulate a problem concretely, like we are looking for eigenvalues of some concrete quantum Hamiltonians, and let us compute them. So, and the computation is in fact quite straightforward, but it requires some calculations. First of all, let us write it in some general form. We have all these expressions are some rational functions of the spectral parameter z. This means that we may, in the general form, write this T of z like this, and then, so let me just write. And this, the expression standing here, or the operators standing here, are the quantum Hamiltonians which we are going to study. Why this formula is true? In fact, it's quite easy task, because you have here this matrix G, and each Lax matrix is 1 plus something. And this 1 plus something is this expression, which has some simple poles at different points. And what you have here is just a product of all these expressions with some simple poles. And what is written here is just a representation of these rational functions in the form of the sum, where you have a sum over all possible simple poles with some residues. And these residues are exactly the quantum Hamiltonians we are going to discuss. But we would like also to have some, yes, and what we know, of course, we know that T of z commutes with itself. This follows from RTT relations. And it means that all these Hamiltonians also commute with each other. So our final problem, first let us write a kind of plan. We will find concrete expressions for these quantum Hamiltonians, and then we so we need to solve a quantum problem in this form. We are going to find these eigenvalues for these quantum Hamiltonians. What we know is that these some maybe complicated operators, but these are just commuting operators. Okay. So we formulated previously we formulated the quantum problem as follows. We have this T of z, this T, And the action on psi should be equal to some t of z without hat. And we were looking for this expression. And this expression it should be understood as a kind of generating function of eigenvalues. This is a generating function of quantum Hamiltonians. It is an operator. And this is just some concrete special function which generates all possible eigenvalues. So let us let us first find, and then also looking at this formula, we may write that that our quantum Hamiltonians are just residues of this t of z at points. And the corresponding eigenvalues, which we are looking for, these lambdas, can be written in a similar way. These are just residues of t of z without hat. So this is our task. And let us then begin with first with computation of these quantum Hamiltonians. We are looking at this expression. And we are going to use this formula. Let us just write it like where we want to compute residue of the following expression. Yes, and maybe it's better to write. We also used, when we discussed the quantum Lax matrices, we also know that these quantum Lax matrices are in fact quantum R matrices. So we may also write it like this. So this is our definition of quantum Hamiltonian. Now what we know? We know that the residue sits on one concrete term standing somewhere here at jth place. Yes, because each Lax matrix or each R matrix has different poles. What we use here is inhomogeneous model, which contains these inhomogeneity parameters, and this allows us to make computation a little simpler, because this residue sits at this jth place, and then it means. And we also know residue of this concrete term. This residue is exactly eta multiplied by permutation operator. Yes, this is the residue of the Lax matrix. Let me write. somewhere here, the residue of this expression is equal to eta multiplied by permutation operator. This follows just from definition. So then we continue writing here. And what we have, let us write it in some detail. We have here trace, and then we have a product of our matrices I just substitute, just let me write and then I comment. This is the first set of our matrices which were standing before this jth element. Yes? And I may substitute here, instead of spectral parameter, the value of the pole, just because they don't contain any poles at this point. Then here I should put the residue of this G-star matrix, yes, and then the rest of the product of our matrices. And the rest of the product is as follows. It begins with this value of index, with the G plus 1. And goes up to end. And the last one is 0n, like this. So now, now we are looking at this expression and we want to calculate it. What we mean by calculation? Yes, maybe yes, that's okay, but maybe I should divide it by eta in order not to have it here. Maybe slightly different. Oh yes, that's true. I should divide it by 1 eta, because our definition included this eta as a multiple, as a factor here. So I just now want to remove this eta from here and from here. But it's just, this is just for a small simplicity. But, so what I want to do, I want to make something just to exclude this zeroth auxiliary space, and I want to have an operator which acts on the Hilbert space only. In order to do it, we should use some properties which we previously discussed, in fact. Properties of permutation operator. Maybe I should recall it. So when you move the permutation operator, say for example to the left, then it changes this component. Let me write it like here. If you have some, say, matrix A in the zeroth component, and you multiply it by permutation operator, then it is equal to A J E0J. Yes, this is the formula which we used when discussed tensor notations. This is why, this is what I'm going to use now. I will move this permutation operator to the left and change all 0 components to jth component. And this is the first action I am doing. So first, let me write it like good to write. Next, like this. And all this is multiplied by this line. The second line is not changed up till now. So what we did, we excluded the 0th component from the first line. But next, we know that this is a trace in the 0th component. So we may change the order. We may, how it's better to show. I want to move all this expression to the end of the product here, because I can change the order of this expression and this expression of the first line and the second line. And then again, after I do it, I again move this permutation operator to the left. So let me, this is equal to what? It is equal to so once again, we moved all this expression in this line here and then move this permutation operator again to the left. So, this means that our answer will begin with this term now. So first we have here RG, G plus 1. Next, a product up to RGN. And then I rewrite here all this expression which was moved to the right. And now what we obtained? We obtained that our expression is free of indices of this auxiliary space except for this term. But it's only a single term. So when we know that if we have some expression of this form, then the trace over, so we have in fact two formulas. You may compute for this expression the trace over G's component, then you obtain A in the zeroth component. But you may also compute this expression in the zeroth component, then you just obtain A in the Gth component. So it's just the same. So it means that I just may remove this operator from this product and remove this trace. And this is the final answer. This is our answer for quantum Hamiltonian. So all these quantum Hamiltonians which we introduced here are operators of this form. Acting on the Hilbert space. This is in fact a quite interesting expression. So you see our calculation just changed the order of indices. Now the first indices are j and j plus 1, then j up to jn, and then it begins with the beginning, j1 and up to j minus 1. The same structure of operators exist, for example, in the so-called quantum Knyzhnik-Zamolodchikov equation, which we maybe will discuss a little later. But so it's maybe not so simple to look at it on the blackboard, but if you do it in your paper, you will see how it works. Okay, we defined the operators. Now we would like to answer main question, what are eigenvalues given by algebraic Bethe Ansatz. For this purpose, we should also recall how we used our formulas for Bethe Ansatz. For the yes, let me recall that the eigenvalue was given in the following form. This eigenvalue T of Z, which was here, yes, the eigenvalue for transfer matrix, generating function of eigenvalues. It was given by this expression. Let me just write and recall the notations. So our notations was as follows. We used short notations for matrix elements of the Lax matrix. We defined it like alpha eta, beta eta, gamma eta, delta eta. Then yes, everything depends on the spectral parameter. Then what we say? Then we say that this alpha acts on vacuum vector by some number function. So the vacuum vector is the eigenvector for this alpha, and the same for delta. And we may now look at this look at this concrete expression. Where is it? Concrete expression for the Lax matrix. Maybe I can write it once again here. So this is just rewritten form for 1 plus eta over z minus zi multiplied by permutation operator. For this reason, we know concrete expression for this alpha and for the delta, which is standing here. And let us write it explicitly. So this alpha is just and tau delta is equal to 1. This was a definition of the action of matrix elements of Lax matrices to vacuum vectors. Then we introduced these functions A and D small, which were products. So we had products of all alphas. But this time, besides the product of Lax matrices, we also have this G matrix, and it also gives us input here. So this A will contain G1, the first component. This G, let me recall that this was just a diagonal matrix, G1, G2. And this G1 comes here in the same way as it comes from all these alphas. The expression, concrete expression for the matrix D, or for the function D. Yes, and now we can write it explicitly. We may write that what we have here is just G1 multiplied by a product z minus zi plus eta over z minus zi. And for this D, we had the definition as a product of functions delta, which are equal to 1. And this is why we finally have here only G2. And this G2 is this element of the twist matrix. So now we have two concrete expressions for the function A and D. And we also need to write expressions for these lambdas. These lambdas were just I should write it here. For these lambdas, we had the following expressions. These lambdas were equal to products of the functions f where this m small goes from 1 to m, where m was the number of these beta roots. So it's a number of turned spins. And we also know explicit expression for this function f, yes? I wrote it already, but let me recall it again. For this function f, we wrote explicit expression in the following way. So now we may substitute it here also. This gives us a product from 1 to m large. Um minus z plus eta over um minus z. This is it. And the difference between lambda and lambda tilde was just in changing the order of these arguments. So this is why we may write it like just here. A concrete expression is given by a similar product from 1 to m large of vice versa, z minus um plus eta divided by z minus um. So at this stage we have all objects. We have all these 4 functions. And we may calculate the residue of this function t. This is what we wanted to do, in fact. We defined the Hamiltonians in such a way that their eigenvalues are exactly residues of this function t of z. And this function t of z is given here. And the residue are taken at these poles, which are inhomogeneous parameters, this zg. So let us look at all these expressions standing here. You may easily see that, for example, these functions lambda and lambda tilde do not contain poles at these points zj. They contain poles at beta roots only. So there are no poles here, there are no poles here. And there are no also poles here, because this is just a constant. So the only non-trivial input into our answer comes from the poles of function a. And this allows us to obtain the result. So we may just let me write it like residue of t of z at point zj. It is equal to what? So we are looking, first of all, we are looking at the first term only, because the second one do not contain the input. And the poles is in function a, so we are looking here and calculate the pole at concrete zj. This gives us, just let me write it. This gives us J1, a product of over k not equal to j zj zj minus zk, zj minus zk plus eta. So I excluded one term, one factor from this product just because I computed residual. And then I should also put here expression for this lambda at point zj. And this is I'm writing here minus eta, while here I have plus eta, just because I changed the sign. Changed the sign. Yes, I wrote z minus u minus eta divided by z minus u. So because here I have z at first place. And this is the answer for eigenvalue. So we found this expression for these quantum Hamiltonians, and these are eigenvalues for these Hamiltonians. And the last thing we need is to write equations. Is to write Bethe equations. But Bethe equations are in fact written in universal form. I already wrote them in the beginning of the lecture. So there is no problem just to write it without any problems. This was just a of u divided by d of u, and then it was equal to a product of say C not equal to M F of UM this was Bethe Ansatz equation, which where m goes from 1 to m large. So this is a set of equations which I used just for finding this set of u's. And then you find this set of u's, for example, using computer, and then put them into this expression and obtain the final answer. So the only thing I want to write, the last one here, is just to write this, just the same equation in this concrete case. And this is as follows. So from left-hand side we have a product from 1 to n large to number of sides, and here we have u. Let me write it in a little different way. U gamma zk plus eta divided by u gamma minus zk. okay, not U gamma, but it was UM. And it is equal to a product of over alpha, which is not equal to, or for example, over C, which is not equal to M, from 1 to M large, of U M minus UC plus eta over UM minus UC minus eta. And this is again the same set. I mean, the number of equations is the same. The number of equations is just equal to the number of beta roots. So we have a closed set of equations. We have explicit form of Hamiltonians, and we have explicit form of eigenvalues. So this is this is a set of famous formulas for this rational XXX chain, which in fact can be generalized and extended to very different situations. For example, they may be they may be extended to trigonometric models, elliptic models, supersymmetric models, and even more. Just during our lectures, we discussed the case JL2, but you may also look for more general groups, at least JLN, and write, for example, the set of equations will be very similar. Then you are dealing with the so-called nested Bethe Ansatz, not just Bethe Ansatz, but nested Bethe Ansatz. But the form of equations is very similar. So if you know expressions in this case, then you will easily understand the structures standing behind some more complicated cases. Okay. So now how much time do we have? And also, it is also important to mention the model, which is called Gaden model, and which appears from all this construction in a special limit when eta is small. This situation is called Gaden model. I just don't know where to write. These Gaden models can be studied. Originally, they appeared in quantum case. What's it called? But they are very well known at classical case as well. It's also a kind of famous example of classical integrable systems, not only quantum. So let us write what happens in this situation. We also, besides considering this limit just explicitly in all these formulas, we also parameterize this twist matrix as so it was G1 and G2, but let us now write it like exponent of eta multiplied by some diagonal matrix. So I mean, our limit includes also expansion of this twist matrix also. So it means that G is equal to 1 plus eta multiplied by V. Let us discuss the Godin limit coming from this explicit expression for quantum Hamiltonians. So let us just write it schematically. Schematically we have, our R matrix, just once again, our R matrix is 1 plus eta over spectral parameter, yes? So this is and this eta becomes now a small parameter. So what we have here, yes, multiply it of course by permutation operator, and let us write it like 1 plus eta multiplied by classical R matrix, because this, as I told you, the first non-trivial coefficient in the expansion of quantum R matrix is a classical R matrix. So instead of writing all these explicit expressions, I will write it schematically. Schematically we have, for example, for the first factor, we have 1 plus eta r j plus 1. I won't write arguments because they coincide with the numbers of corresponding tensor components. Then we go up to 1 plus eta r j n. Then we have this twist matrix, which is, as we told, 1 plus eta v. And now the last line, it also just contains product of r g1 and so on up to 1 plus eta r j minus 1. In fact, we want to compute only the first non-trivial input. So it obviously, this expression begins with 1. And now it will contain some eta by something plus etc. And we are looking for this something. So for coefficient behind the first power of eta. How it arises? It arises from the sum of all these R matrices, in fact, of all these R matrices and this diagonal matrix V. Because when you consider, if you have two R matrices, then this will be the second order, yes? So this is why I can write here the following answer. So this for this Hamiltonian of quantum spin chain, we use decomposition, not decomposition but expansion, I'm sorry. And the first non-trivial term of this expansion is what is called Godin Hamiltonian. Godin Hamiltonian. So the number of Godin Hamiltonians is the same as the number of spin chain Hamiltonians. And let me write explicit expression for this it's a sum for k not equal to j up to m. R jk or just we may now use explicit form of our classical R matrix, which is a permutation operator divided by spectral parameter. Then it comes like V plus P jk divided by zj minus zk for sum over k not equal to j. So this is a definition of Gaden-Hamiltonians. This is a general definition which includes some classical R matrix, and this is concrete definition of a rational model, J invariant, where we just have this permutation operator divided by difference of spectral parameters. Yes, and we may ask ourselves why Gaden-Hamiltonians commute with each other. So in fact, it follows, of course, from this limiting procedure, but it is interesting also to mention that if you compute this commutator, then the result will be 0 due to classical Yang-Baxter equation for these classical R matrices. So we have a commutator of two sums of classical R matrices, and they will, so I will just schematically write that they will unify in these combinations. And these are exactly the combinations which we know from classical Yang-Baxter equation. And so at classical level, we have this equation as a condition for the Jacobi identity for classical R matrix structure. So it was a kind of definition of classical integrability. And now, in this case, we have this equation which gives us commutativity of quantum Gaden-Hamiltonians. That's just an interesting trick. And of course, you may consider the limits of all these equations, and they are easily written. Maybe let me write some example. For example, eigenvalues for these Gaden-Hamiltonians will be given in the following way. They will have, let us also, I wrote here V1 and V2, but let me change it into V minus V in order to have a zero trace. Then eigenvalues for Gaden-Hamiltonians may be written like some h divided by zi minus zk. This is a solution in our concrete case, in the case of JL2 and rational R matrix. Yes. So this is a set of eigenvalues. They depend again on the set of beta roots, and these beta roots satisfy a set of beta equations. And the Bethe equations are also no problem to write down. 2v plus a sum from 1 to n h u alpha minus zk, and it is equal to h, the sum u alpha minus u gamma, and here again alpha goes from 1 to n large. So we're assuming that we're in the same situation as in spin chain, so we have m turned spins. So the formulas for Gaden models for Gaden model can be written in a similar way, and maybe next time I will also explain some relation of these formulas to classical models of Gaden type, and I also should comment, and maybe we will discuss it separately, that when you have a set of these Hamiltonians, which are called Gaden Hamiltonians, you may also consider a set of equations and this set of equations is known as Knizhnik-Zamolodchikov equations, and they came from the studies of conformal field theories, and it was interesting. It was interesting how they are related to Gaden models, because here we study a stationary Schrödinger equation. And this is a kind of non-stationary Schrödinger equation. So the Knizhnik-Zamolodchikov equations can be viewed as some kind of non-stationary generalization, so non-stationary version of Gaden model. And I think we stop for today.